It's raining, it's pouring, puddles are forming. It's raining, it's pouring, go do something bold.
Hello, I'm Karen Redmond, Chair of Waterloo Region, and on behalf of Waterloo Regional Council, I would like to welcome you to Waterloo Wellington's Children's Groundwater Festival. Groundwater is central to Waterloo Region. We depend on it. Groundwater provides over 80% of our clean drinkable water, and it also allows our farms, schools, and businesses to function. It also reminds us how connected and dependent our region is on the natural environment. Science and nature take our groundwater on an incredible cycle through our community. I hope everyone in attendance has a fun and successful festival. Please share the message of Groundwater Festival on social media and share how important groundwater is to you and to our region.
Hi everyone, it's Mayor Cam Guthrie from the City of Guelph, and welcome to the Waterloo Wellington Children's Groundwater Festival. And I really appreciate that I'm able to bring greetings on behalf of the city to all of you that are joining. And you know what, as the mayor of Guelph, I just want you to know that the conversations around water are actually very important to me. In fact, Guelph is one of the largest cities in Canada that relies on groundwater. We don't have a lake or a river that we can access for water in that way. And so groundwater is important to take care of. There are sometimes some risks, and so we have to be super careful on how we deal with our water in Guelph. Now, the cool part is that the people of Guelph and the businesses of Guelph actually really know how to take care of our water. In fact, the people of Guelph use 30% less of the daily amount of water than any other Canadians because we know how to conserve it so well. I'll give you one quick example. We introduced a new way of cleaning all of our transit buses by actually capturing all of the rainwater to wash the buses, and that saves alone 1.9 million liters of water a year. And so that's just some of the neat stuff that we're doing here in Guelph. So have a good rest of the day, enjoy the festival, and remember to always conserve and take care of water no matter where you are. Take care, bye-bye.
Welcome to the virtual Waterloo Wellington Children's Groundwater Festival. My name is Kelly Linton. I'm the Mayor of Centre Wellington and the Warden of Wellington County. I love the Waterloo Wellington's Children's Groundwater Festival. For the past 25 years, this festival has brought experts together to talk about the importance of water to our lives and our communities. That is something that will never change. No matter how much life changes around us, no matter what new technologies are invented, water will always be one of our most essential resources, right up there with air. Local government leaders are tasked with protecting and safeguarding our water. I take this responsibility really seriously. I want to wish the festival and all the students who attend this great virtual event all the best. Enjoy all of the Groundwater Festival posts on social media, and please share them with your families and friends. Have a great time.
I volunteered for the festival the first year when I was in grade 10. As a high school student, one of my teachers brought me to the festival knowing that I was interested in the environmental field. During that first visit, I learned quite a lot about groundwater and the impact that it has. And I continued volunteering for the festival for another 8 or 9 years or so after that. And it really did lead me down the road I'm on today as a career in groundwater resources and groundwater remediation.
As a water professional, the Groundwater Festival is very important to teach young children and even the adults that come and volunteer with them about our water resources, the groundwater that they drink on a daily basis, and the importance of conservation of this program. It allows us as the City of Guelph, as well as the other member municipalities, to feed our messages about preservation and conservation and resource management through a variety of different fun and exciting games that the kids actively enjoy and play in, as well as the volunteers have a great time.
So it's important to have events like the Groundwater Festival because in Southern Ontario we're very blessed with what appears to be an abundance of water. and it seems to be an unlimited resource. And I think at an early age, it's important to teach that water is not an unlimited resource, and it's a finite resource that we need to take care of and care for into the future.
Well, hello to everyone joining us for day 3 of our virtual Groundwater Festival. My name is Michael, and I am coming to you from the Ken Sealing Waterloo Region Museum, where if it were normal times, we would be collecting together and joining here, and in our historic village here. But unfortunately, it is not normal times quite yet, and we are needing to meet virtually, which is okay. We're going to make the very best that we're able to for this festival. But before we begin, and I kick things over to my friend Kevin, I'd like to take a moment and acknowledge the people who were in this area and throughout Canada, throughout Turtle Island, for many, many years before us, for thousands of years. Those indigenous communities, which included the Haudenosaunee, the Anishinaabe, and the Neutrals people. Those people took care of the land and the water here for generations before us, and those people are still here. And they have knowledge and they have wisdom that they want to share and are eager to share with us of how we can preserve nature and make sure that we keep our air and our water and our land clean. I'm going to show you a map. This is a map of the Haldimand Tract. And the Haldimand Tract is an area of land on 6 miles of the Grand River, both sides of the Grand River. It's shown in white on this map. And this land, the Haldimand Tract, it was promised to First Nations people just about 250 years ago. But that promise was never fulfilled. And all that those folks got were the lands that you see represented in yellow on the map, the Six Nations settlement. And so I bring this up today because we're talking about rivers and waterways and the Grand River. And I'm also bringing it up so that you know and you're aware of this. Because in future, we're going to have to be thoughtful and thinking through how it is we respond to those promises that were made to Indigenous people, and how we're treating those communities now, those communities which are part of our community. So do some thinking on that and ask yourself about rights to land and rights to water and looking after those things. With no further ado, I'm going to turn it over to my friend Kevin. Kevin, over to you.
Well, many thanks there, Michael. I hope you're having a good day, sir. And good morning to you all. And thank you so much for joining us here at the Waterloo Wellington Children's Groundwater Festival. We have a great day lined up for you, and we have all sorts of activities centered around the topic of groundwater. We're going to actually explore what groundwater actually is and why it's an important source of drinking water, as well as, okay, how do you get groundwater, which is located way, way down deep underground? How do you get it from down there to your home? It should be a really good day. And I'm sure the day is going to bring up some questions that you'll have. Well, we have a chat room. And in that chat room, we have all sorts of fine people who actually know all about groundwater. So if you have any questions or even some observations, just type them into the chat room and you'll actually get an answer to your questions. And, well, social media being what it can be sometimes, we do have some rules that will govern our behavior in the chat room. Well, don't worry, they're dead easy. Basically, we're looking for good common decency. We're looking for you to be respectful. Well, what does that actually look like? Well, I'll give you an example. It's something like just use language that you would normally use around your teacher and your parents. And another example would be, don't make nasty comments about other people's answers or questions. Yeah, there's just no room for that today, because we want everybody to have a really good time while you're here with us today. Now, just in case things do go off the rails a little bit, we have people in the chat room, including Levi, the enforcer, who has the quickest timeout hand in the land. And he'll just put you out over to the timeout area. But we're not going to need that today, are we? Because I know all of you can be good, kind, decent people. And we're going to have a good time while we're here. Well, enough of that. It's time to start the festival, and we are going to start with our first trivia question of the day. And that question is, what material makes up an aquitard? I'll repeat that again. What material makes up an aquitard? And we know that one's a little hard, so we actually even have a clue for you. It's something that you might find if you're digging in the ground. Maybe something like sand or rock or clay. So give it some thought and type it into the chat room if you think you know material makes up an aquitard. And we'll take up that answer very soon. But first, we're going to learn a lot more about groundwater.
Hello everyone, my name is Karina McDonald. I work at the University of Waterloo's Earth Sciences Museum. Did you know that depending on where you live, some or all of your drinking water comes from groundwater? Groundwater forms when rain or snow melt seeps through the ground, like soil, sand, gravel, or rock, and is held in those spaces in the ground. I have some gravel here in front of me. If I hold it as if it's really compressed underground, you can still see that there are spaces between the gravel. That is where the water is stored and where the water can flow through. Here's an example. I've got soil here in my garden. Underneath the soil, there's gravel, just like the stuff I'm sitting on. I have a container here full of the same stuff. I just take off the lid. I've got soil in the top and gravel in the bottom. See? Let's take a closer look. When it rains, the water moves through the soil spaces and is then stored in spaces between the gravel. All of the water underground stored in those spaces is what we call groundwater. Have it. Groundwater. Now that we know what groundwater is and how it moves down into the ground, let's explore how groundwater moves through different earth materials. Let's explore the amazing aquifer. Come on, let's go.
All right, thanks, Karina. So now that we all know what groundwater is and how it moves down into the ground, let's explore how it moves through different earth materials. Years ago, all of Waterloo was buried underneath a huge glacier that was hundreds or even thousands of meters deep. It was roughly equivalent to 4 CN towers tall. That is a lot of ice. Now, these glaciers were dirty. They were full of sand, gravel, and other stuff. And about 12,000 years ago, that ice melted, and as it did, the stuff trapped in the ice, remember the sand, the gravel, and the clay, was all sorted into layers hundreds of meters thick. This model is very similar to what is below our feet in Waterloo region. So here are some of the wells. Here's the river. This would be like the Grand River. Here's the lake. This might be like the lake in Victoria Park. And this is the stuff underground. These are artificial structures that we put there. Now there are several layers in this model. At the surface, this green stuff is meant to represent vegetation. So that would be the plants and the grass, the trees. And below that layer, there's some coarse gravel, and then some fine sand, and then some coarse sand, And wedged in there are some clay layers. If we were to follow well 1 all the way down, you'd notice that it runs into something, and this is meant to represent the bedrock. In Waterloo Region, the bedrock is dolostone and limestone, and it's highly fractured, and these lines represent those fractures. In some places, like Lower Gorge, the bedrock is near the surface, and you might see this if you went for a walk in that area. But in other places, it is hundreds of meters underground. This is a core of the bedrock from Waterloo, and you can see here that there are fractures, and in these fractures, this is where the water is held and where it would flow. This is what makes it an aquifer. Of course, sand and gravel also hold water and allow it to flow, so these are also aquifers. Some material, like clay, is exceptionally slow at letting water flow through it, and so we would call that an aquitard. It's slowing the flow of water. Alright, so now we get to do the fun part. We're going to show you how water flows through this system, and to do that we're going to use dye. I'm going to invite my assistant over, and she's going to actually apply the dye. So everybody, this is Alba, and we're going to give her the syringe. Here's our blue dye, and she's going to squeeze it and suck some blue dye in, and she can add a little bit to each one of the wells, these first ones here. Go for it. Yeah. The height of the water underground is what we call the water table. So in here, you can see, because Alba's added blue dye to all these different wells, we can now see where the water table is. I'm going to use this red pen, and I'm going to connect the river to the depth of the well, the water in the wells, to the lake, and we'll see visually where the water table exists. And what you notice is that it's not a flat line, that it follows topography to some extent. The depth of water underground changes depending on where you are. That's pretty important if you're a farmer or if you live in the country and you need to get your water from underground. You want to know how deep the water is, so you know how deep you're going to drill. The height of the water underground also changes with time and with precipitation. And at the top here we've got a pump that's pushing water through our system, and it's over here on the right in our area of recharge. This is where the water, when it's raining or when the snow melts, water enters the ground. So right now it's raining. If I move the pump over, it stopped raining. And you can see, you should see in a second, the blue is going to start dropping in each one of these wells. So as the rain decreases, the amount of water entering the system decreases, and the amount of water underground decreases. So here you can see it's well below that red line. And it's going to keep dropping the longer we leave it on. Of course, it'll eventually rain again, so let's bring this back. And wow, look how fast that is. There's a good rain event, a nice thunderstorm. The ground is going to quickly recharge. One of the other things that I thought we should explore with this model is how the water enters the system over here, but it exits over here in the river. So this water is flowing from one side to the other. Now, we've got several different layers, several different aquifers. The water is going to flow through them at different speeds because of the pore spaces, because of the size of the material. So the gravel, it's pretty big material, and that means the spaces between those materials is quite large as well. So in theory, if the spaces are larger, the water is going to flow faster through that. Up here in the sand layer, the particles are smaller, so there's smaller spaces between the particles. That means water can't flow quite as fast through it. So if I was to guess which of these 4 layers the water is going to flow the fastest, I would guess that the fractured bedrock is going to be the fastest because the pore spaces are the largest. And this fine sand layer at the top is going to be the slowest because the particles are so much smaller. There are other layers like this clay layer. They're going to act in a different way, but we'll come back to that in a minute. So I'm going to add a little bit more dye, and then we're going to flush it. We're going to see which one flows the fastest. Now remember, theory is that the water's going to flow really fast in this one. And look, follow Alba's finger. It's already flowed almost all the way to the other side. Number 2, it's only about halfway. And in number 1, or sorry, in this one, it's only moved a little bit, maybe 2 centimeters. So the size of the material is really important for how quickly the water flows. And fractured bedrock is the fastest, fine sand is the slowest, and then these cobble and gravel and coarse sand, they're in the middle. All right, so we've cleaned up the flow model, we've flushed it out, it's nice and clean now. We're going to show you one more thing with this flow model. In Waterloo region, we get most of our drinking water from underground. And it's important that we don't contaminate it, that we don't put something in it that might make people sick. Unfortunately, it's hard to imagine how we could pollute the ground and the groundwater because it seems solid. But it is possible to put stuff into that groundwater that we don't want to drink. And a flow model like this is a great way of showing you how that can happen. So let's do that now. All right, so we've zoomed in so you can see this part of the model better. This is where the artificial structures are. In our model, we have a septic tank, which we're not going to get into, and then an underground storage tank. This is something you would find at a gas station. And this is where the gasoline is stored that we put into your cars. Now, unfortunately, sometimes they can get a hole in it, and if that happens, that gasoline is going to leak slowly into the ground. I'm going to use red dye to demonstrate this. So in our example, red, it would be the gasoline. Okay. So as I add the red dye, I want you to think about where it's going to go underground. Okay, so put it in the chat. Is it going to end up in the septic tank? Is it going to end up in the lake? Is it going to come out in one of these wells? I think it might make it all the way over into the river. Wow, look at that. So it's moved all the way over into the river. Now the river is turning red. So that gasoline that leaked out of the underground storage tank was able to flow down and deep underground, flow all the way down into the river. Incredible. Some of you might be wondering though, why didn't it go down into the coarse gravel layer or into the fractured bedrock? So if you think you know the answer to that question, put it into the chat. You might be wondering, is there anything we can do about this? If an underground storage tank leaks and we don't want the oil or whatever the contaminant is to get into the river, how can we clean it up? Well, thankfully we have these wells. Perhaps we can use a well to clean up the contaminant before it gets in the river. So let's flush this model out. We'll contaminate it again, and then we'll use well 5 here, and we'll see if we can't suck the pollutant out before it gets in the river. Okay, now while that starts to flow, we're going to use this syringe with this tube here to act as our pump. And we're going to connect it to well 5, and we're going to draw water up out of this gravel layer here. And we'll see as the plume gets closer, we'll see if we can't suck it up and keep the contamination from getting in the river. So it looks like if we can keep pumping, we can pull the contamination out of the ground before it gets in the river. What's happening because this well is in the middle of what we call a plume of pollution. Because we know which way the water's flowing, we can predict which well we could use to collect the wastewater. Now, I haven't been pumping quickly enough because a little bit of the waste has ended up in the river, but a lot less than if we'd done nothing. You can see how the pink is getting less and less. The water is getting cleaner. So you can also pump from the site where the contamination is entering the system, and you can add clean water. And this is what scientists would call pumping the water out and treating it and then returning clean water back to the system. Well, I hope you enjoyed this amazing aquifer and learned about how water flows through different materials. Think about this model during the next activity. Bye, everyone.
Now that you know what groundwater is, and you've seen it moving through different earth materials in the amazing aquifer, our next activity is all about building your own aquifer at home. Follow along as we build an edible aquifer, and enjoy.
For this next activity, you will need a jar to hold your aquifer, some clear pop to represent your water, some ice to represent your gravel, some food coloring so that we can see our water, some ice cream as our clay, a type of cereal as your sand, cookie crumbs to represent soil, a gummy bear to represent life, some juice crystals to represent pollution, and a straw as a well. Okay, let's do this. So first we need our ice as gravel.
The ice cubes have spaces between them, just like gravel does, and acts as an aquifer.
Next, we need our pop as water.
The pop fills all the spaces between the ice cubes, just like water fills the spaces between gravel in an aquifer.
If there's little people in your house, they may need a bit of might need a hand for this stuff. Next, we need our clay, or ice cream. Oops, I forgot to add the blue dye to my sister's aquifer. I'll add a bit to mine. Once you've added your drop of dye, swirl it around. Next, we need our clay or ice cream, which I've already done for my sister.
The ice cream acts as a barrier and slows water down, just like clay does.
Next, we need our sand or cereal.
The cereal is like sand and lets water flow through it.
Next, we need our dirt or cookie crumbs.
Soil, or dirt, supports plants and animal life. Water can also flow through it.
Next, we need our life or gummy bears. So now, finally, we need our pollution, or juice crystals, which could be oil, gas, or bad bacteria.
Just because groundwater is underground, it can still be affected by what we do on the Earth's surface.
Next, we're going to see what happens to our pollution when it rains.
Rain and snowmelt can transport pollution down through the dirt, sand, and cracks in the clay and into the groundwater. Let's see that again.
Look it! It's coming down into the aquifer. It's coming down. Luckily, we have wells that can clean up our aquifer. Come on, stick in your well. Down. Help. Let's clean up our aquifer. Yummy. Thanks for joining us. I hope you enjoy your aquifer.
Well, thanks so much there, Karina and Levi. Nicely done. Only problem is I now have a hankering for an Aquifer sundae. Don't really need that, however. Well, before we move on to our next activity, let's take up our answer to the first trivia question, which was, what material makes up an aquitard? Now, if you said clay, you'd be bang on. Now, in an aquifer, where you find groundwater, it might have a layer of clay, and this layer of clay is called an aquitard. Now you know. Well, since we're on such a roll, why don't we go on to our second trivia question of the morning, and that is, what is another name for a pipe put in a hole to extract groundwater? And I'll repeat that for you. What is another name for a pipe put in a hole to extract groundwater? Man, these questions, they're getting harder with every passing day of the festival. Well, for our next activity, we're going to learn about how groundwater gets from deep down in the ground to your sink at home. Peter, how is that actually done?
Hi, I'm Pete, and I'm here to talk to you about wells. So a well is a hole that's made in the ground for the purposes of locating groundwater, or to test the materials, the gravel or the rock, that the groundwater comes from. So the earth acts like a sponge. It rains and it snows on that sponge year after year. And the water, the rainwater or the melting snow, soaks into the ground. And eventually, at some point beneath the ground, all the spaces between the soil particles are filled with water. When they're shallow and it's close to the ground surface, they're filled with air. But when you get to a depth, certain depth, they're filled with water. And at that point in time, we've encountered groundwater. It's like when you're at the beach. If you dig a hole beside the shoreline and you start to dig, the hole is empty, has no water in it. But if you dig down deeper, then water comes into it. So the shallow soil, all those sand particles are filled, the spaces are filled with air, and beneath that, they're filled with water. So I'm going to show you a video of water coming out of fractures in a rock. So this video shows how the water is coming out of a very discrete or a specific fracture. They're not flowing through all the fractures, not flowing across the whole same fracture. And this is what we need to do. We need to drill wells into the ground to locate that groundwater. Then we can use that groundwater for drinking or washing or for supplying water to our our communities. So I'm going to talk to you about 3 different types of wells today. We're going to talk about dug wells, we're going to talk about monitoring wells, and drilled wells. Now, all wells have the same 2 things. That's a casing and a lid. So the casing is what keeps the hole open. When you drill a hole into the ground, you have to hold that hole open. And they have a lid on it to protect things from falling down into it. So we'll talk about dug wells first. So dug wells are large diameter, large width. They're about 1.5 meters wide sometimes. And to hold those large holes open, we either use concrete cylinders, or sometimes those wells, those holes are actually lined with stones or bricks. And the water flows slowly into them from the bottom. And we use the water during the day, and then during the nighttime, the water comes back into the ground. One of the issues with these dug or bored wells is that they're fairly shallow. They're maybe 10 meters deep or even shallower in some cases. And because they're shallow, the water quality in those wells could be impacted. They might have bacteria in them. They could have fertilizer if they're in the country. They could have road salt if they're near a road. So sometimes the water quality in those wells could be impacted. Another issue sometimes with those wells is the lids of those wells. Sometimes over time they can break. So the pictures that I'm showing you now are pictures of things that have fallen into wells. And sometimes people fall into these wells. So we have to be careful that we maintain these wells so that the lid stays secure and nothing falls into them. So the next type of well I want to talk about is called a monitoring well. And a monitoring well is a smaller diameter or smaller width. It's only about 15 millimeters or a centimeter and a half or 2 centimeters in diameter. But we can drill these to all sorts of different depths. The purpose of these wells are to let us measure water levels and collect water samples from different depths. So this next video is a video of Jeremy showing us how we measure water levels in our monitoring wells.
So my name is Jeremy, and today I'm at a quarry. I'm here to conduct some groundwater monitoring, which involves taking water levels and groundwater samples. So beside me here you can see a monitoring well. Now this well is just a white PVC pipe in the ground with a cap on top so that nothing can fall in. This well was constructed before the well regulations were put into place, and so it doesn't have a protective casing around it. Wells that you would see today, they would need to have a protective casing. So this well is drilled to a shallow depth, and then beside me we have a well that's drilled to a deeper depth. And what this allows is for us to understand how groundwater moves in this area. So what we're going to do today is take a water level out of this well. So taking a water level is a fairly simple task. We'll start by taking off this J-plug that's protecting the well. And then we're going to take this water level tape, and all we have to do is insert this probe down the well. When this probe reaches the water, it'll send a signal up the tape and it will beep. So let's do that. So you can see it measures to 88 centimeters on the tape, and now we need to bring the tape up to find the meter mark so we can get an exact value for our water level. So you can see there 3 meters and 88 centimeters, 3.88 meters is our water level in this particular well, and that is measured below the top of the PVC pipe. So always remember to seal the well back up to maintain its integrity, and then record your data in your field book.
So the third type of well I want to talk about is a drilled well. So we're here at my farm where I live outside the city, and I have a well. And you can see the well, it has a lid, it has a black steel casing. In this case, this well is about 25 meters deep. And you can see the lid, it's secure so nothing can fall into it. So drilled wells tend to give us better water quality because they're deeper and the water that we're taking is further away from the ground surface, so we aren't going to typically have some shallow contamination that affects them. So they supply all the water that we need. We have a pump in the bottom of the well that pumps water into the house. Some of our communities rely on drilled wells, like the City of Guelph and the region of Waterloo, and in this case, these wells are a larger diameter and deeper than my well, and they produce much higher quantities of water. So while my well might provide 20 liters a minute, these municipal wells can provide 2,000 liters per minute. So the video that we've got of some municipal wells inside of a well house where you can see these large diameter wells and some of the equipment that we use when the water comes out. Now there's one more type of well I want to talk about, and that's called a flowing artesian well. So water flows into a well because of pressure. The water pressure is higher outside the well than in the well, and it flows in. And when we pump water out of the ground, we create low pressure, so water comes into this well. Now sometimes the pressure is so great beneath the ground, it forces the water all the way up the well casing and out the top and out the surface. So groundwater is something we have to protect. Wells are one of the ways that we take groundwater out of the ground, but they're something that we have to maintain and keep safe so that our water quality is good for us to drink and that we don't take too much water out of the ground. Thanks for joining me.
Well done, Peter. Thank you very much there, sir. It's really neat to think of a well as being one large, long drinking straw, isn't it? Only problem is, again, now I have a hankering for a very large chocolate milkshake. Again, something I don't really need. However, it's time to turn our attention to something actually quite serious. And you may have already read about communities that don't have access to clean drinking water. And as a result, these people are getting sick from their water. Now, it's really important that the water that we consume is tested. And it goes through a battery of tests, especially in Waterloo Region and Wellington County. Now, to learn more about how we actually do test the water, we're going to turn to Kyle because he knows all about it.
Hi, I'm Kyle, and I'm an environmental scientist, and I'm here today to talk to you about why we sample water. So we're going to talk about 4 different types of water today. We're going to talk about tap water, we're going to talk about groundwater, and we're going to talk about wastewater, and we're going to talk about stormwater. So first we're going to talk about stormwater, and behind me today is a stormwater pond, and this stormwater pond is used to partially treat pollutants that come off our roads and parking lots, like salts and bacteria and even dirt. So some of the sampling that we do with stormwater ponds is to make sure that the pond is working as designed or as engineered. And we take samples on usually big long bottles in bottles, and take samples usually as the water's coming in and as the water's flowing out of the pond to make sure that the pond's working properly. So the one thing with stormwater ponds that you must remember is that even though they look like ponds that might be fun for skating or for swimming, they're not. They can actually be very dangerous, so you need to make sure that you stay away from them. And there's usually signs like this posted to tell you to keep off. Hi, now we're going to talk about groundwater and why we sample groundwater. First, we're going to talk a little bit about how we sample groundwater. So inside these blue metal pipes are monitoring wells, so they're groundwater wells, and these wells go deep into the ground beneath us, and groundwater is of course the water that's underneath us in the soil and rocks. So how deep do these wells go? Well, some of these wells can be as deep as a telephone pole is high, and some can even be as deep as the water tower is high. So why do we sample groundwater? We sample groundwater to find out if it's contaminated or if it has any pollutants in it from different activities like gas stations or road salt or other industrial activities like that. And how do we sample it? Well, we sample it with a couple different things. We sometimes sample with pumps, and sometimes we sample it with a special piece of equipment called a baler, which is almost like a long, narrow bucket. And other times we use something called a foot valve, which is what I have in my hand. And it's just got like a little ball there, and we attach a big long hose to it, and then we can move it, and the water goes in through the valve and pushes up through the tube to the surface, but it doesn't go back out because the little ball stops.
Okay, now we're going to talk about tap water. So tap water, whether it comes from a municipal drinking water system or whether it comes from your own private well, is the water that we drink. So it's very important that we make sure that we sample drinking water to make sure it's safe to drink. Now to do that, the municipality, if your water comes from a municipal system, they sample your water daily, and sometimes multiple times a day, and they do that before it comes to your tap. But if you have a private well, so if you live in the country or if it's at your cottage, and you have a private well, then it's the homeowner's responsibility to sample that water. And to do that, you use these sample bottles right here that come from the public health unit, and you take that lid off right there, and you fill it up from your tap. All right, we have a little exercise here to demonstrate to you why it's important to sample tap water, whether that's private water, private well water, or municipal water. So this glass full of blue beads represents our glass of water, and when a sample, like the sample bottle in the back, is taken to a laboratory and tested, what they do is they take part of that water and they run it through some laboratory instruments to test for the presence of different contaminants. And one of the contaminants that they do look for is bacteria, specifically E. coli. And now E. coli can be found in lots of different places in the environment, including our food, and it can make us sick. So it's very important to make sure there's no E. coli in the water that we drink. So for this exercise, what we're going to do is we're going to take a look at this glass of water, and it's got blue beads in it, and we'll take a little bit of a sample from it, and we will look to see if there's any red beads, which represent the E. coli. Now this glass of water in this part of the sample does not appear to have any red beads, so therefore this water would be safe to drink. Now here's a different glass of water, also with the blue beads, and it looks the same as the last one, so it looks like it's probably safe to drink, right? Well, not necessarily. This is why it's important that we sample, because we can't see bacteria, we can't see E. coli with our eye. So although this glass looks like it's okay, when we do our sample, our test sample again, and oh, right there, we find a red bead. We find some E. coli. So that just is to demonstrate to you that it's important, and there's another one right there in the glass, that it's important for us to always get our drinking water tested, whether or not it's municipal, and in that case the municipality does that for you, or whether it's your private well at your home or your cottage. It's always important to get it tested, and you can do that if it's a private well through the health unit and a sample bottle just like that.
All right, now we're going to talk about wastewater sampling. So what is wastewater? First of all, wastewater or sewage is the water that comes from your sink or from your toilet, and it goes down into pipes under the ground and ends up at the wastewater treatment plant. And this is a wastewater treatment plant in Elora in the township of Center Wellington, and Grace is an operator at this plant, and she is going to show us how she samples every day. So this first video is Grace taking a sample of the wastewater as it comes into the plant. Now we're taking a look at the bubbles in the aeration tank, and wastewater plants have lots of different pieces of equipment to clean the water, and this is one of them. Grace is now grabbing a sample with the sludge judge from another piece of the treatment process called the secondary clarifier, and she uses this to get down to the bottom to get a sample at the very bottom of the clarifier, and then she transfers that into the bucket. And they use this to test the treatment process. And the secondary clarifier gives the solids in the water a chance to settle out before it goes to a polishing step, which is called the sand filters. And now we're going to watch Grace take a final effluent sample after the sand filters. So there it is right there. And you can see how clean and clear that water is. Grace is now in the laboratory. Grace is looking into the microscope to look at the microorganisms that live in the aeration tank, and these microorganisms help treat ammonia, which is poisonous to aquatic life. And finally, we have a picture of the first sample that Grace took when the wastewater first came into the plant, and that's on the right-hand side, and a picture of the final effluent after it's been treated and just before it gets discharged into the Grand River when it leaves the plant. And you can see the difference between the two samples. That's why it's so important to ensure that all of the solids and toxins are removed from the water before we discharge it to the river.
All right, thank you everybody for listening. I hope you learned lots about sampling water, and I hope you have a great time today at the Waterloo Wellington Children's Groundwater Festival. Thank you very much. Have a great day.
That was great, Kyle. Many thanks to you, sir. Wow, it takes a lot of work to test our stormwater, our groundwater, our drinking water, and even our wastewater. But sure glad there are people around who actually do that, though. Well, it's time to answer our second trivia question of the morning, and as you will recall, that was, what is another name for a pipe put in a hole to extract groundwater? Well, if your answer was a well, you're right. In fact, municipal wells can be anywhere between 30 and 90 meters deep. That's the same height as a 10 to 30 story building. Now that's one large drinking straw. Well, we've met a few people already this morning whose job it is to look after our water supply. And we're going to take time now to meet another person who's has a watery profession. So, with more on that, over to you there, Sue.
Well, welcome to the Career Corners of the Children's Groundwater Festival. it takes a lot of people to make sure that our water is clean drinking water, and that once we've used that water that it gets flushed down the toilet, and sometimes we need to make sure that that's all taken care of and cleaned as well. There's a number of dedicated people working in the water industry, and we're going to take a few minutes to hear some of their stories. And today we have with us Andrea. Welcome, Andrea, to the Waterloo Wellington Children's Groundwater Festival. And thanks for joining today and sharing your story and what your job is in water. So I'd like to have you start and tell us a little bit more about your job title and what might a typical day be like for you in your water job.
Yeah, well, thank you for having me. This is really exciting. I'm always excited to share what I do. It's a passion of mine, which is water. And so I'm an assistant professor at the University of Waterloo. I'm in the Department of Earth and Environmental Sciences. And my job as an assistant professor is predominantly teaching students at the university about water and getting them ready for their careers in water, and also doing research about water, studying it. And so I focus mostly on groundwater, but also on what we call groundwater surface water interactions. So if you go outside and see a stream that's running in your backyard or in a park, it doesn't just hang out there by itself. It's connected to the ground. It's connected to the water in our subsurface. And so a lot of what I do is study how those are connected, because different things affect them both, like what's inside of it, whether it's contaminated or not, or how much is actually going to be there. So a typical day for me right now, since we're doing this interview in Zoom, of course, is not what a typical day would be in most other years. So right now it's a lot of Zoom meetings. In normal, it would be meeting with my students. So I have students who are doing various different degrees with me at the university. Some of them are doing research. Some of them are just going through their courses. So whether I'm teaching them in a course, I'm meeting them and helping them with assignments, kind of like teachers do in high school and elementary school. And then I also have students who I'm helping through their research. And so that's where I'm guiding them in discovering, their new little bit about water. And when I do my own research, the students are part of it, but it is really involved, like I said before, this groundwater surface water interactions. And for the most part, I do all of this on computers. And I don't spend a lot of time going out into nature for my job and collecting data or taking measurements. But what I do is I use and I make computer codes that will simulate this, that will say if it rains in a certain area, how much of that water goes into the ground and replenishes our aquifers, replenishes those storages of water under our feet, or how much runs off and ends up into our stream. To do this research, there's really three main parts of my job. And the first one is this research isn't free. I have to go and find people who will give me money to do it. And so that involves writing proposals. So my job is not just doing science, but being able to write and to express what I want to do. Then if I find someone to give me money, I get to actually do the research. So whether that's going out and collecting some field data that I do sometimes, or writing different codes, or using different software. And then the last bit is communicating that. So when I find something new and interesting, I go and I write papers that we publish to show other researchers, or I go and I give presentations, or I come to things like this to talk about my research. So that's the main parts of my job.
Oh, that sounds really interesting. So it sounds like you need a love of water and an understanding of some technology behind it to bring it together, which our next question was, how's your job connected with water? And I think that you answered that already with the connection that you made to that it's not just groundwater, it's the interaction between groundwater and surface water. So on our groundwater day, that's pretty impressive. What do you like most about your job?
I really love two main components of my job. And so that's actually why I ended up. So as a university professor, I've only been in this role for a couple of years. Before this, I worked as a scientist for a government agency in the United States, in the state of Kansas, one that most people don't know where it is, but it's right in the middle of the country. And the two components I like is I love the research. I'm really curious. I want to know more. I want to figure it out. I love writing software and code and making it do and write in these simulations. But I also really like teaching. And so my other job with the government agency was a little less involved with students and with trying to teach it, and it was more with research. And so the component that I really like about my job now is I get to do the teaching. I get to teach courses on water and methods that we look at water and analyze water. And I get to interact with my graduate students and help guide them in their research and their proposal writing and their thesis writing. So that's the two parts that I really like, is being able to satisfy my inner curiosity and also trying to engage other people and get them excited about the same stuff that I am.
Well, I think you have a whole audience out there that's going to get very excited about water. Are there any cool tools that you get to work with during your job? And you know, if you do, what might you be using them for?
So, as I said, I don't tend to do a lot of what we call field work, so going out and collecting measurements. But when I do, one of my favorite tools to use is what we call an infrared camera. And so this is a camera that, rather than your phone, or if you're older like me, your camera, that takes a picture of what you see, an infrared camera takes a picture of the temperature of everything. And so if you take a picture of a group of people standing outside in a forest, if it's, you know, sort of fall or spring, what you'll see is our skin is really hot and the ground tends to be cooler. Our clothes are even colder than our skin because it's connected sort of to the atmosphere. And so you see these images. What I use that for is, since I'm interested in this groundwater surface water interactions, if I take a picture of, say, a stream or a stream bank or a lake, we can see if there's temperature differences between our groundwater and our surface water, which there is a lot of time. I can see where that water is coming in. So a quick example is, if it's the winter time, the surface water, if it's not frozen, is cold, right? It's connected to the cold air around us. But our groundwater is under our feet and it's insulated a bit, right? It's like imagining, you know, you dig a hole in the ground and you live in that cave as opposed to out in the air. It's a little bit warmer in there. So our groundwater stays warmer. So if I take this infrared camera and take a look, and I see areas where the water, the stream bank or areas of the stream are warmer than others, I can tell that that is where I'm having that groundwater surface water interaction. What I do most of the time is write code. And so the tool I love is any coding. And so that is, I use Fortran, which is a very old one, but also R and Python and any coding language where you get to basically tell the computer what to do and to run these simulations, I find to be really exciting.
Yes, that I think has an interest for a whole bunch of our audience, whether they're science lovers or a computer and the coding part, which is really important as well. So what training or what education did you have before coming to the job that you now have?
Yeah, so I typically, to work as a professor at a university, you need to get your PhD. So I did finished my high school degree. I did an undergrad degree in engineering, and then I did a master's degree, which is sort of your first level of graduate degrees. And then I did a PhD. So you typically need to get a PhD. As I mentioned, I then went and worked for a government agency for a little bit before I had this position. Some people go and work for other researchers at universities, and that's just a good way to try to learn not only how to do the research and manage your own projects, but also get some involvement with teaching students and helping them with their research.
So definitely a love of learning. What inspired you or helped you to decide that this was what you wanted to do today?
So I'm originally from Northern Ontario, a couple hours north of North Bay. And so I grew up on the side of a big lake, surrounded by trees, surrounded by rocks, and also surrounded by a lot of forestry and a lot of mining. So a lot of things that use our earth and use our water to allow us to have the quality of life that we have, to allow us to have cars and build houses. And so it was pretty early on that I realized that I love nature. I love water. I'm fascinated by it. I'm fascinated by how everything interacts, but that I'm also fascinated by how we use it and how we need to try to balance the two. I do want to go canoeing and kayaking and hiking and rock climbing, but I also want my car to get me there, and I want to live in a house that I can heat. And so how do we do both of those things? And so that's where I ended up really interested in something that brings it all together, which is water. And a lot of my research is not only looking at this groundwater surface water interaction, but how can we manage it so that we can go hiking and make sure that we can take care of all of the animals and the ecosystems that water supports, but also support the other things that we've now become dependent on.
Great, thank you. Do you have any other final words that you want to share with our audience?
I guess my only final words are just, make sure you stay curious, make sure you pay attention to stuff around you, ask questions, take opportunities to understand if there's something you really enjoy, ask more questions about it. You will find more careers are out there than you'll ever hear about in school or see on television. And that if there's something that you enjoy, like a corner of water or trees or anything, there is a whole bunch of different careers out there that you can pursue. And you can find something that you're truly excited about that can also help you pay your bills. So, aside from staying curious, just make sure you stay safe right now.
Well, thank you, Andrea. I think that you gave us a nice snapshot of what you're doing at the University of Waterloo, and that your curiosity, your love of nature, and your love of coding led you, to a path that you have a job that is truly remarkable. And we thank you for, doing that, and the research that you do, and just understanding the interaction with groundwater and surface water is so fascinating and so important to us every day when we're using water. So on behalf of the Waterloo Wellington Children's Groundwater Festival, thank you for sharing your story today. I'm sure it will inspire some of our friends that are watching today. Thank you.
Thank you so much for having me.
Oh, thanks to you both, Sue and Andrea. Much appreciated. It is amazing just how many people it takes to keep our drinking water safe. And given a few more years, maybe one of those people could be you. Something to think about. Well, we've got a great way to finish off our morning here at the Groundwater Festival, and that is with a story and a song. And the story, it sounds like an interesting one because it features a worm and a water droplet. And its title is Wally and Deanna's Groundwater Adventure. So, let's have a listen.
Wally and Deanna's Groundwater Adventure to the Saturated Zone. Story by Leon Appleby and Peter Russell. Illustrations by Fortunato Restaño.
Story read to you by Peter Russell and Karina McDonald.
Wally the worm popped out of the ground carrying his knapsack. "It's a great day for an adventure," he exclaimed. The clouds were starting to gather. Looks like rain, Wally thought as he wriggled faster and faster across the field. High above Wally in the clouds, Deanna Waterdroplet and her friends gathered for a new adventure. Wally looked up just as Deanna was about to land. He put out his hands to catch her. Other water droplets splashed around and percolated into the ground.
Imagine Deanna's surprise that she wasn't percolating. "I'm Deanna Waterdroplet, and I must go on a groundwater adventure and percolate with my friends."
"Percolate?" asked Wally.
Deanna bounced from Wally's hands and explained. "When water droplets slip and slither into the ground, it's called percolating. Would you like to come along?"
"Wait for me, Deanna." Wally pulls out his shovel from his knapsack and quickly dug into the ground.
It was easy digging through dry, sandy soil. Then the soil started to get heavier.
"My, this is hard work," said Wally. The hole began filling with water. "I've never been through the water table before," said Wally. He quickly put on his breathing mask so he could catch up with Deanna. "This is easy digging through," Wally said as he pushed the pebbles aside.
"Welcome to the saturated zone, Mr. Worm," said Deanna.
Please call me Wally.
All right, Wally, said Deanna. Take a look around. We are now in a gravel aquifer where all the pebbles are surrounded by water. Deanna's friends passed between gravel pebbles and then fine sand grains. They twisted and bumped as they moved through the aquifer.
Wally dug and dug as fast as he could through the fine sand, trying to keep up with Deanna.
Wally and Deanna reached a layer where the water droplets had been sitting around for a long time.
What's this stuff, Deanna? Wally asked.
It is an aquitard, Deanna explained. When the grains become very fine, they are called silt and clay. The spaces between the grains in an aquitard are so small that water droplets cannot travel through them. Some of the water droplets try, but it takes a long time.
As they continued their adventure, they started moving faster near a tube in the sand.
Help! Deanna shouted. We are being drawn into a well.
A well? Asked Wally.
Some animals up on the ground surface put a metal tube into the ground and take water droplets out, said Deanna. One of the animals, called Mr. Martin, was filling a bucket with water for his pigs to drink. Some water droplets bounced over the top of the bucket to percolate into the aquifer once again. They safely passed the well. My friends are seeping out of the aquifer into a stream of water droplets, said Deanna. Can you swim, Wally?
No, Wally replied.
Well then, Deanna said, let's go up to the unsaturated zone again, where your friends live.
Oh, fresh air. It stopped raining, said Wally as he took off his mask. They popped out onto a nice warm rock. How long is this adventure? Wally asked.
Not long this time, Deanna explained. If we had been traveling at the same speed as my friends, it could have taken from weeks to many years to reach here. Deanna started to get that warm, light-headed feeling. Oh, I'm evaporating, said Deanna. Don't worry, this is part of the adventure. See you again soon.
Deanna evaporated as water vapor faster and faster up into the clouds. Thank you, Wally called out. Thank you for a great adventure. Come back soon. After Deanna had evaporated, Wally pictured their adventure in his mind. He now knew how the water cycle worked and was sure he would see Deanna again. The end.
Well, the weatherman said you better stay in bed. It's another gray, rainy day. Everyone despair, there's water in the air. It's gonna wash your smiles away. All the plans you made will have to be delayed because of this H2O. Everyone hide, you have to stay inside. There's nowhere you can go. 'Cause it's raining, it's pouring, puddles are forming. It's raining, it's pouring, go do something boring. Well, the stuff we need to live is falling from the sky. No time to celebrate, hang your heads and cry. Farmers might say that showers are a blessing, but we've been told that rain should be depressing. So shut down all the playgrounds, close the summer camps. Imagine what would happen if the children got damp. Hide out in your houses, hide out in your cars. If you want to find some water, go look for it on Mars. 'Cause parents all know, and you should not forget, the worst thing that can happen is if something gets wet. It's raining, it's pouring, puddles are forming. It's raining, it's pouring, go do something boring. then you better stay in bed. It's raining, it's pouring, puddles are forming. It's raining, it's pouring, go do something boring. It's raining, it's pouring, puddles are forming. It's raining, it's pouring, go do something boring.
Well, thanks for the real toe tapper there, Sean. Much appreciated to you. Well, I'd like to thank all of you for joining us today here at the Waterloo Wellington's Children's Groundwater Festival. And just a reminder to you fine folks that today's proceedings were actually recorded, and we're going to be sending out a link to you via email to all the registered attendees. And I'd also like to take this moment to extend an invitation to you all to join us again tomorrow at 10 o'clock for the Groundwater Festival. And tomorrow's theme, it's going to be an interesting one. It's all about water technology, which includes toilets, which should be really fascinating. And we've got a whole host of activities lined up. It should be a good time. So I hope you can join us. But until then, bye for now.